Welcome, everyone. I'm Jacob Strauss. I'm a principal engineer at AWS, and today I'm going to talk about a block storage system that we built as part of Amazon's Elastic File System. I've been working on EFS for a couple of years now, and looking forward to sharing a little bit of some of the things that we had to build and some of the things that we learned along the way. So EFS is a cloud-native file system. And I think it would actually help to describe what a cloud-native file system is before we get into too much further. So there are a couple of different properties that we like to use when we're talking about a cloud-native file system. And these are all described from the end customer's point of view. So one of the properties that ends up being important for the use cases that we built EFS for is that it be elastic. We don't want to have customers have to think about how much space they need in advance. We want to give them the ability to create an empty file system, write data to it, have it grow and shrink based on what their use cases are, and not have to plan in advance for what that process is going to look over time. And along with that, we don't want customers to have to think about managing infrastructure or provisioning space. Sort of all of those are all functions that we want to shift from end customers having to think about to having us as operating these file systems as a service to think about instead. Similar properties around the way that we price things and the ability to create things quickly. Now, just as we need to be able to shrink capacity storage, we also need to be able to scale throughput on demand when end file systems need that ability. So that covers sort of the not only the space used but also throughput to that file system. And the third component, which I'm not going to talk today much about particularly, is that a cloud-native file system is integrated with other cloud services. So in our example, since I'm going to be talking mostly about AWS, that includes things such as the ability to access file systems from virtual machines in Amazon EC2 or functions in AWS Lambda, containers, things like that. So let's move on to sort of start working through a deep dive into the block layer that we've built. And to get started, we built a block layer specifically for EFS. It's built out of actual physical drives in the end, and that's sort of what I've shown here on the slide in a setup. So we've got what I'm showing here is we've got two different file systems. This is sort of the view from the file system and then its implementation in the backing store for it. And then we've got a block store that's built out of a bunch of disks that are distributed in some fashion. And next, I'll go through a few properties that we need from this setup. So one is that the two most important tenets that we think about when we're designing and operating EFS is security and durability. And there's sort of you can't have one without the other. So what do I mean by what does security mean for a block layer? One of the things that actually means a lot of things, but one of the things it means is that we need to make sure that a operation that comes through file system A gets their data and only their data back, and file system B sees the same thing. It sees data for only its own content and can't mix up data between the two of those. Whereas in terms of durability, things break all the time, and so what I've drawn here is on the slide here, if we have two disks that fail, we still need the ability to get the data, the end data off of those drives and make those accessible to the file systems that are relying on that particular set of blocks. So another property that we need is we need to make these file systems highly available, even in the face of permanent failures such as I'd shown before, and that really end up being a durability question, but also more transient events that you can think of as an availability failure. So in the common way of describing this is a network partition. So here what I've drawn is two disks that are partitioned off from the rest of the system. Now, of course, in reality, it's usually not this clean a distinction between this particular drive can't talk to anyone else. You often see very messy combinations of things that look like they're succeeding and failing and changing all the time. So we need a system that gracefully handles those kinds of events. So then a third set of properties that we need when we're thinking about how to build a block device are more around how do we name things? How do we organize this? Do we carve it out into saying everyone every file system gets a dedicated portion of a system, or do we think about this as operating as some larger, sort of more uniform system that's shared across lots of different uses? Then within that, how do we think about naming? How do we think about locating? So if I'm working on an operation for a given file system, how do I figure out where the data for that file system operates, where that file system lives? Then there are a bunch of questions around what exactly are the operations that the block layer has to support. So some obvious ones to start with, that we need to be able to read and write individual blocks. We need some way of allocating space and clearing out free space in the end. But there's a couple others that we're going to actually add into this that I'll come back to later. Now, the third set of properties of the block layer that we've chosen to put there is being responsible for determining the order of events in the file system. And I'll come back to this topic in a little bit. So as I mentioned early on, how we want to build file systems that scale in an elastic manner. So that means that the block layer itself has to scale in an elastic manner. We need the ability to go from a system that has some number of disks in it, and then transparently and continuously transform that into a system that has a much larger set of devices in it. And the reason for that is we need the file systems that are using that block layer to scale without having to be involved in terms of what's going on in the block layer itself. So let's switch now to talking a little bit about how we go about building this block layer. And the first thing we're going to need a data structure. We're going to need a couple data structures, really. But spoiler alerts, we're talking about blocks here. Basically, the only data structure I'm going to invoke today is an array of blocks, and we'll build everything else off of those. So what we're going to do is we're going to create a structure called an extent. It means something that's a little bit different from what an extent is in many different file systems. Here, it's really just an array of blocks that are of a fixed size. So sort of in practice, they're a couple gigabytes, though it varies in terms of exactly what those are. And what this allows us to do, it allows us to come up with a uniform naming scheme for all the blocks in a system. So I can just name. So let's say I want to refer to that third block in extent A. I can just think of the overall block address of a tuple of the extent as sort of the name of the extent and which block within that extent. And similarly, I can do the same thing for some other extent. And then once I've got this, if I want to grow the system, if I want to make a larger system and sort of scale up the amount of storage I have, all I have to do is keep creating extents. So as long as I can come up with new extents and new names for them, I've got a uniform sort of shared address space that I can use across an entire service here. So, but now let's sort of switch and talk a little bit about how we actually implement an extent. So what is it? So clearly we can't just have an array of blocks, or rather we can have an array of blocks, but we need to decide how we are actually going to implement it. And what we choose to do is say that every extent is itself, it's a replicated state machine. So we use, and the way we're going to make changes to these extents is that we're going to send all operations through a consensus protocol. In practice, we use Paxos, but from this point of view, you could very well use Raft or chain replication or anything, or approaches like that. You would get a same result, but sort of slightly different. Details would be slightly different. So what I've drawn up here is showing a logical view of what we think of an extent is, and we sort of split it into two pieces. You don't. This is a not always the way that everyone builds replicated state machines in Paxos, but this is how we think about it. In that we think about it as having one set of state, which is this is sort of the traditional view of what Paxos is copying around, and then off to the side there are blocks that are really where we store the data for the extent. But these are both sort of the core part of the logical view of what is an extent. So now switching gears, sort of going one layer deeper when we talk about how do we actually store one of these things on a drive somewhere. They're split in two different pieces. So if we look at any individual disk that's participating in an extent, there's two components in there. One is just a log of operations. And so this is, you can think of this, an operation, examples of things you would find in an operation log are write this block, allocate this block, and then there are more specialized things, which I'll come back to in a moment. And then off to the side, there are shards of data. So one of the differences between the way we build in a replicated state machine is that we're not fully replicating everything across the replicas. Instead of saying, we need this data, here are the operations we perform, and here are the blocks, and at the end we want to end up with n different identical copies. What we do instead is we want to end up with n different erasure-coded shards of the same data, so that we don't have to store as many full copies of the data. So that if you look at that two different replicas that are hosting data for a particular extent, the operation log, sort of the sequence of events that occurred to that particular extent, those will be identical, sort of at least once you get to the point of all the different copies of that extent are caught up and have the same data. But the block shards, those will end up being different. So you need to, in order to reconstruct the data that's stored in that extent, you have to consult enough, you have to retrieve enough copies of those shards and then go through an erasure decoding step there. Some of the extra operations that live in the operation log are things that are more around editing the state of the extent itself. So in our system, the extent itself is the authoritative source for who are the members of the extent. So for example, if you want to change which servers are replicas of that extent, what you end up doing is you write an operation, sort of perform a Paxos operation that says, here was the old set of members and here's the new set of members, and you have to get a quorum in both sets of the membership and things like that. So other examples of things that end up being in the operation log and then are in that state portion of the extent that I talked about before are things we need to keep track of in terms of knowing which ones of the replicas are caught up, which ones are still collecting data that they don't have yet, things like that. So the next topic I'm going to go through in terms of how we actually make use of these extents is where do we decide to put the replicas? So what we do is we make use of a concept that AWS has called availability zones. And what these are sort of separate data centers that are in separate power domains. They're linked together by high-speed dedicated networks, and they're distributed around a given metropolitan area. So the goal of placing these things is that they are far enough such that they won't be subject to the same sorts of power events or localized storms, things like that. But they're close enough that you can still do synchronous requests and responses from one availability zone to another. So what we do is we take the replicas of a given extent and we distribute them across at least three different availability zones. And then, as I said before, so we're using Paxos and for these operations. And the way that works is that at any point in time, there's a special replica that has elected itself to be what we call it as a proposer for for that extent. And they're the ones that decide the sequence of operations. And then they see if they can get a quorum of the rest of the remainder of the replicas to agree on what those operations are. So if we think about an overall request response cycle looks like, a request arrives at the proposer, and then it sends a set of messages out to all the replicas. And as soon as it gets back a quorum of responses from the replicas, basically saying, I've written this particular request down in my operation log, it's durable on disk, I can respond. That's the point at which the proposer says, great, this particular operation happened, it's durable, I can send a response back to the caller and say they're good to go. If it doesn't get a quorum of responses, then it gets more interesting. So as I mentioned before, so let's think about what happens if we have a network partition here. Let's say the proposer can't talk to anyone else in that extent at some point in time. So at that point, one of the other replicas will notice that eventually it will notice that this has happened, and it will elect itself the proposer for that extent. Well, as soon as it can get a quorum of the other replicas to agree that it's now the new proposer, we can send requests for the extent there, and it can make progress quickly. So this gives us a quick response to immediate events that affect whether individual replicas are reachable, whether they're reachable right now, whether they come back, and so on. And if a given replica in an extent fails permanently, it's exactly the same procedure. The only thing that's different in that case is that once we discover that that one of the replicas is missing, and it's been missing long enough that it's probably broken, then we can go ahead and replace it, sort of add a new member to that extent, and then copy all the data back that is stored in that extent over to that new replica and restore the sort of full availability, full durability of that extent. And all of this is transparent to the upper layers. None of the callers that are talking to this extent have to know that any of these that this process is happening. All they have to figure out is who is the current proposer for this extent and how do I find them. And that's a much easier problem to solve because it doesn't require very much data to keep track of who do I think is the current proposer for this extent, or how to get redirected to one if you have a stale view of where the proposer is at a given point in time. So the slide that I was describing just before this on availability zones is one of the techniques that we use to make the system resilient to certain types of failures. And next I want to talk about another type of approaches that we take to add resiliency into the system. And you'll see that if you look at the diagram on this slide, it looks very similar to the prior one, but it's actually talking about a sort of a division of responsibilities that's a bit different. So here what we've done is we've said, instead of having one copy of our block storage system, we make a bunch of smaller copies. And we call these cells. And then we take individual resources, or in our case here, we're talking about file systems, but they would be other things in other services. And then we assign them to a given one of the cells in particular, and then route all the requests to that particular cell. And this ends up with a nice property where if something goes wrong in one of the cells, it won't affect things that are going on in other ones nearby, even though they're basically the same. They're the same setup. There's nothing that's inherently different about them. And the reason that we take this approach is to try and reduce the blast radius of a given system that we're operating. And you'll see this term used in a bunch of different places. One of the challenges of this is that you end up with an inherent tension between wanting to make the cells as large as possible, because then you get sort of the best utilization, best cost savings, or best ability to sort of distribute requests across a larger pool of sort of back-end resources. But you end up with a larger blast radius. If you think about if something happens, then you think about which which end customers, which end users are going to be affected. It's a larger group. There's more opportunities for things to run into trouble there. So if you instead shrink the cells as much as you can get to you get very strong isolation between those boundaries, and sort of deciding where that point is one of the more interesting things we have to work through when we're designing and operating these services. Okay, so now I'm going to switch gears and talk a little bit about how the callers of this block system make use of sort of what the requests that we send. So as I mentioned a couple slides ago, we're talking about blocks, so there's a read and write interface, but we extend this to support conditional writes. So you'll notice up here, so if I want to read a given block, what I will get back from the block store is not just the data that goes along with that block, but I'll also get a version number that describes sort of where the extent was when that read occurred. And the thing I can do with this version number is that I can pass it back when I want to modify the same block. So I can then say, let me write the same block with some new data, and I'll also say, I'm assuming that the contents of this block hasn't changed since the version that I sent in before. And what we have our extents do is they validate that given block hasn't changed at all across between the associated read and the associated write. And if so, it performs the operation. If not, it just sends back an error response instead. Now, what this lets you do is you've basically built an isolated sort of atomic view sequence of operations to a particular block. So and you can build this out of this simple conditional write sequence here. But it's not good enough to build a file system with just this set of operations alone. We need to add one more, and we call this a multi-block conditional write. This is a way I've drawn it here is listed as a multi-write. But the way that you make use of this is that you read a bunch of blocks, you keep track of what versions you got back from each one of them, and then if you want to edit all of the blocks at the same time, you can then call this multi-block conditional write and pass in, here's the blocks I want to edit, here's the new data for them, here's the versions at which the reads occurred, and if the block store determines that none of those blocks changed in between the reads and the associated write that I'm in the process of performing, then it will go ahead and carry out all of those writes atomically. And again, if not, it will send back an error response. And the reason that I have that the write responses also return a version here is it's often convenient to say, let me perform a write and then immediately go ahead and perform some other operation. So examples of places where we use that are cases where we get partway through an operation and discover that we need to allocate new blocks to sort of expand or shrink something, and then we commit some set of operations and then go back and again use that immediately to perform some other set of operations. So this set of these three operations are basically what we need in order to build a file system that spans different blocks and have those blocks span different extents even. But it's not quite the way that it's convenient to write a file system layer. And so what we did there is we created a little library that lets everyone who's performing file system operations, so things like how do I add a link to a directory, or how do I append some new data to a file, things like that. They get to use the style of operations that I've drawn here on the right, where we have an explicit begin a transaction, inside the context of that transaction, read a bunch of blocks, perform local modifications just in memory in the caller that's deciding what the file system modification is going to be. And at the end, once it's got to a consistent view of those operations, send a commit request. Now, if you think about what those operations are, and which ones, sort of how these correlate to the operations that I've listed on the left side of this slide here. Read blocks, they're just mapped directly to the block layer read operations. But the commit operation at the end is a multi-write. It's a multi-page conditional write. And it has this pattern where if the commit succeeds, then that means that this operation actually happened. Whereas if it fails or aborts, that means that the operation didn't happen. And an operation can abort for basically any reason. But one of the most common one would be that one of the blocks was actually changed while the caller was sort of in between the read and the associated write request. And in that case, that means that the conditional write will fail in the end. So if you look at this, this is a form of optimistic concurrency control. There's no explicit locks of blocks here. What the callers are doing is assuming that there's no contention for the given blocks, reading them, writing them, and at the point of the write, that's the point where it discovers whether there was anything contending for those underlying blocks or not. Okay, so as I mentioned very briefly just before, file system objects, or at least the things that we may need to edit as part of these operations, can span different extents. So how do we actually implement this multi-block conditional write? So it is a form of a transaction, and we choose to implement it as a type of two-phase commit. But it's a little bit different than maybe the traditional view of a two-phase commit. What we do is we actually break it into a transaction chain. And so the caller that's performing the file operations will sort of gather up all the operations that sit as part of this multi-block conditional write, and then figure out which extents are involved, and then send the original request to the first extent in that sequence. So in here, I've drawn that as extent A. Extent A will perform its little check to say, has the block changed since the associated read happened? If not, then it will write some data down in the extent itself. So this is in the state part of the extent, basically things like there's a transaction in progress, here's what it is. And then send a prepare message to the sort of down the chain towards the end of the chain. And each extent in this phase will perform that same sequence of checks. Is this request valid? Does it conflict with something? If not, write it down and send the request along until you get to whatever the end of the chain is. And which is I've drawn it as extent C on the slide here. And that's the point where we decide whether the operation as a whole succeeds or fails. If you get to the end and nothing else conflicts, extent C will say, great, this operation actually happens, and it'll write down a commit. It'll sort of perform the commit operation. At that point, we've decided the eventual fate of the operation, and everything that happens after that is just letting everyone know that it's actually happened. So the extent C just sends commit responses back up the chain, and extents B and A can go ahead and perform their actual operations. So let's talk a little bit about sort of what properties we get from having transactions in this scheme. So one of them is that there's no centralized coordinator for the transactions here. So if we have two different transactions and they have no extents in common because they're operating on completely different data, then they won't even be sending messages to the same extents. So there's no dependence on them. So that means we get some great scaling properties here. This is a form of this is turning an optimistic transaction into something that's actually using locks. It's so in between the point in time where an extent decides, I'm going to start working on this transaction, it's valid, I'm going to write it down, I'm going to perform the prepare operation, it has to wait. It has to block operations on that particular block until it learns from down the chain in terms of what the eventual fate of the operation is. So it has to get a response, either a commit message or an abort message saying this thing didn't actually happen. So going back to the scaling properties, we do get some nice parallelism out of this when you have cases where there's no contention for the blocks themselves, but you notice there are a bunch of messages here. We're actually sending things down a chain. There is a linear relationship between how long it takes to perform and how many different extents are involved in the operation. So the next thing we do have this running in production today. These forms of transactions, but we also have another one. And what we did is we looked at the use cases that customers were running, and noticed that there's a variety of different trade-offs between what they need in terms of latency, what they need in terms of parallelism. And we liked the optimistic model for being able to write the file system definition, but we wanted a lower latency version of that same thing. So what we do is we add another layer in between, sort of sitting between the block store and the upper file system layers. And that layer has two things in it. One of them is it's a cache of metadata of blocks. But the other one is it's a journal. It's a write-ahead log. It's sort of the structure that you would see from any given database. So what this lets us do is you can read blocks through this cache, and if it's present in the cache, it can just return it directly. If it's not, it'll go send a request back to the underlying block store. But what we did is we used the very same interface that the block layer exposes in the version that I described before, so that the file system layer can then send these multi-page conditional writes to this caching journaling layer in the middle, using the same. It's actually the same code running regardless of which one of the configurations we want to use. And what the journal does is it takes that chain of extent operations that it needs to edit and writes them down not in the eventual extent that it's writing to, but in a dedicated journal, dedicated space of a write-ahead log. And the reason that ends up being faster is that it can actually do the journal commit in parallel, even if it ends up having to span multiple blocks there. It doesn't have to wait for that serial set of steps there. So what this gives us in the end is we can use the same file system implementation. We can use the same design, use the same backing storage layer, but we get two different sets of combinations of degrees of parallelism for parallel I/O operations versus latency of performing those individual operations. And we've actually built both of them, and this is the difference between the two file system modes that EFS offers today. Okay, so just to wrap up some of the things that I've talked about so far, we've talked about how to build a cloud-native file system, and in particular the block layer for that cloud-native file system. So some of the properties that we need from such a layer: we need durability, we need security for the end data that we're storing. We need high availability of the block layer. We need to be able to scale the amount of storage that we're making usable to the end file systems. We need a simple interface that's similar to existing block layers, but we've added some things to make ordering of operations easy to reason about. And it needs to be resilient to a variety of different failure modes based on sort of what's going on in the underlying layers. Some of the techniques that we've used in practice in order to build EFS's block layer are replicated state machines. We make use of distributed consensus, including across availability zones. We split the whole system into a cellular architecture, meaning that instead of having to operate one big service, we operate a bunch of different smaller copies of the same thing. It makes operating and reasoning about what properties we're going to get out much easier, and limits the blast radius to should something go wrong. And we make use of optimistic transactions in the definition of what our file system interfaces, and we've built two different implementations of those optimistic transactions, and to give us a different balance of scale out behavior versus lower latency, depending on what's most important for the end applications that are running that are making use of those file systems. So thank you for watching, and hope you learned a little bit about how what some of the techniques for building a distributed block store are. Bye.